Hi, today we'll be covering a new type of problems that usually arise after using separation of variable methods to differential equations, and they have certain forms. So today we cover type of problems which usually we start with the PDEs, and we end up with a form that's known as SLBV form. So, and that's what we're covering today, the SLBV problems or problems. We'll cover different topics and we'll try to draw a big picture out of these. At the beginning, they feel that as they are distinct and far, but we'll try to connect the dots and try to draw a big picture out of these. So we'll speak about the definition of the SLBV problems. We'll move to eigenvalues and eigenfunctions and how to obtain them out of the SLBV problem. We'll speak about the inner product or data product of vectors and then functions. So we'll speak about vectors, vector space, function, and function space. And then from that, I'm speaking about the inner product, we'll move to the Lagrange identity. We'll speak about very important topics, which is how to use the eigenfunctions and eigenfunction expansions to solve ODEs, which is basically a result of the separation of variables that comes out of that PDE. We'll speak again, I already mentioned that function expansion using eigenfunctions. So let's begin. So this is the definition of the SLBV problem. So, and this is the general form that we have here. So I want to highlight that we have this initial form here that we have, and this part here, I just want to highlight that we have this part here, the derivative is with respect to all of that. So that's, if we would expand that, that's just p with respect to x, y prime plus p y double prime. I just want to highlight that these actual derivative with respect to both these and plus this part here, and all of that equal to lambda times certain function r multiplied by y. And the first part here on the left side, usually we call it using this linear operator ly, and that's equal to whatever we have written there. And if that's non-zero, again, the qx part. Many of the problem, this part is zero, but it doesn't have to be. So we have this now, this operator, if we call it this part, now we can say L equal to this part here. And that forms kind of the SLBV problems. Along with the definition of the equations and how it looks like, in order for a problem to be an SLBV problems, we have these conditions that have to be satisfied. That we are speaking about certain interval, and we have to assert that we have certain interval that we are targeting, and that we are assuming that x is just between 0 and a. And we're assuming that this function p here and this function r is basically, both of them are greater than 0 for all x, and they all are real. So this one has to be real as well. And we have two boundary conditions. The first boundary conditions is at 0, and the second boundary condition at a. And I want to highlight that here, this part here is what we call separated boundary conditions. And all what that means, that boundary condition given at 0, it's not mixed with the boundary condition at a. They are independent. So we have the boundary condition at a and the boundary condition at 0 and at a. And they are given here at their very general form, in which we have the function itself plus the derivative of the functions defined. This part can be 0. It doesn't have to be. This p can be 0, but it doesn't have to be. So this is the very general form. So this is the general form of SLBV problem and its definition and how it looks like. Let's move on and try to learn a bit more. And we'll start with the origin of the SLBV problem and where it comes from. And if you remember, when I started, I said this is part of a PDE, which is quite different what we've done during this course, which we mostly covered ODE problems. That it will turn out, as you'll see, that's not too far from what we did, because we'll turn the problem into an ODE. But basically for ODE, we're speaking about a function that we're taking the function of one single variable, and that derivative is taken with only that single variable, which, for example, is the x. In the case of PDE, now we're speaking about another function that's a function of multiple variables. Now we're not speaking about x only, but we're speaking about x, t, y, or whatever values we have in there. So now the partial derivative that we take here would be once, for example, with respect to x, and then with respect to t. And that's the main difference between an ODE and PDE. Now we're speaking about the derivative with respect to multiple variables. And let's explain that further and see where the SLBV problem comes from. Let's take this example here, where we have a partial derivative. We have a function y, and let me highlight here that this function y is a function of x and t. And we have the partial derivative, and it's described by this equation, which is partial derivative with respect to x twice plus y plus y of t. And we want to see how, starting from this point here, starting from this equation, how can we get an SLBV problem or SLBV statement, or the SLBV differential equation anyway. So the first thing that we use separation of variables, and all what that means is that it's, as written below, that we assume that this function here, which is a function of x and t, is separable, and all of that means that it's a multiplication of two functions. Let me write it down there. So it's just multiplication of x times another function that is a function of t only. So this is a function of x only, and this is a function of t only. And we assume that this y equal to this. And usually that t, or that, I mean, this capital T is expressed as e to lambda t. So if we take this one here and the new definition and substitute into that equation, we get the following. So that will just look like this. That would be just y double prime, and that's with respect to x, which is this y now, plus small y plus now the derivative with respect to this one here, where we'll have lambda multiplied by y. And as you can see here, I'm just taking the e lambda t as a common factor so that it doesn't show up here, and that's equal to 0. Looking at this equation here, we can tell that this part can never be 0. So we take the other part, which is this one here, and let me write it into this form, that we have negative y double prime minus y equal to lambda y. And now this part here is nothing but we can rewrite it as this here. So minus y equal to lambda y. This is our SLBV problem. And now, if you remember here, we used to have a p of x, but that in this case, p of x just happened to be a 1. So this is the origin of SLBV problem, and we just now need to add for sure the boundary conditions to it, and that's the origin of SLBV problem, and that's where it comes from. If we speak about major equations that comes in this form, we have the diffusion equation. We have heat equation or heat conduction equation. We have the wave equation as well. The all are types of this class of problems. So This is the origin of SLBV and where it comes from, and it basically came out of using separation of variables to a partial differential equation, and that at the end we end up with this form here. Okay. Now let's move more toward the problems and the type of problems that we usually have and the typical solution type. Again, the shape of problems that we usually cover is more or less have this form here. And probably most of the problems that you see in the homeworks is something of this type here. So it's either that this one here, which is we have this L operator, and we'll come to what that is, and equal to negative y prime equal to lambda y, or this form. And the typical solution of these problems have this form here. If you look at this problem here, this is not far from what you already know. This just looks like just like a normal ODE. And the way to obtain that solution, you can see that you can assume a solution that y1 equal to cosine alpha x. And if you substitute that one into that equation, you will get something in this form, that negative alpha square plus lambda, and that's the cosine alpha x equal to 0, ups equal to 0. And the non-trivial solution, you'll see that, okay, that's just now we have lambda equal to square root, alpha equal to square root of lambda, which is what we have here. So that y1 is a solution, and so that solution just looks like cosine square root of lambda. And if we use another solution, and that solution is y2, and that y2 is sine alpha, and use the same method, you'll basically find that your general solution is just like what we learned, that it's c1 y1 plus c2 y2, which is what we have here. So that's just y equal to a sine square root of lambda, which is what we obtained here from the eigen equation that you already know, plus b cosine square root of lambda x. So that's the general form that we will get, and most of the problems we'll see in this chapter are start with something of this form, and the changes that comes out of that is basically comes from changes in the boundary conditions, and those will affect these constants a and b, or c1 and c2, whatever you call them. Now let's just warm up and try to solve a simple problem and find the eigenvalues and eigenfunctions, and to know what the eigenfunction is. We haven't really spoke about what the eigenfunction is, but let's just warm up and do a simple problem and move on. So again, this is a simple SLBV problem that's described by this form here, and we have these two boundary conditions. And notice that these boundary conditions are separated, and they are homogeneous and they're not mixed. So we'll assume a solution just like what we did before. If you just use y1 equal to sine alpha x, and we use y2 equal to cosine alpha x, you'll find that alpha is basically square root of lambda, and we will find a solution that's y1 plus y2, and that looks like this. We have again a sine square root of lambda x plus b cosine square root of lambda x. Let's try to change the colors here so that we get a bit more excited. So we have this general form, and what we need to do now is basically to apply the boundary conditions. And basically the boundary conditions here, we have y at 0 equal to 0, and that will be just this part now will be 0, and this cosine part will be 1. So we'll have this one equal to just b, and we conclude that b equal to 0. So if we just now rewrite, just to make it clear, now our y is just this form now, because we know that b is 0 now. And let me just highlight now, we will reach that later, that this part here is what we call eigenfunction. So nothing new here, as you can see. And this part is what we find as eigenfunction. If we proceed now, and we'll find the characteristic equation and eigenvalues. And to do it, we'll just apply the other boundary condition. Usually we start with the boundary conditions at 0, so that one of the terms will cancel out and we obtain the eigenfunction. And then we apply the other boundary condition, which is basically y at 1 equal to 0. If we plug that will be just, we'll have a times sine square root of lambda, and that equal to 0. But now notice that in this case, the only non-trivial, if a equal to 0, that's just the whole differential equation is 0, and that's just a trivial solution, and we do not want that. The non-trivial solution in this case is that if this part is equal to 0, so if this sine square root of lambda equal to 0, and this part is what we usually called the characteristic equation. So this one here is the characteristic equation, and you can write it something like this here, if lambda equal to 0. And this part is what allows you to find the values of lambda, because if we take it aside here, so that's sine square root of lambda equal to 0. The only way that the sine will be 0 is basically if the square root of lambda equal to n pi. So where n equals 1, 2, 3, and so on. So, and that's represent our eigenvalue. So we can rewrite our eigenfunction now. Let's use now this definition. Now, if we use our eigenfunction phi, we can write as phi n. That would be just here, will be an or times sine. Rather than writing square root of lambda, now we'll write as n pi times x. And let me, for now, I don't want to write it as phi n. I want to save phi n for the normalized one. We'll come to that later. So, so now we see that we have our eigenfunction, and it's written in terms of our eigenvalues. Let's do another quick example and move on. So there's another example, and we basically have this differential equation with these two boundary conditions. And if we do the same thing, we will basically find that y equal to, again, a times sine square root of lambda x plus b times cosine square root of lambda x. When we apply the boundary conditions, we'll find that at 0, that's just equal to b. So this part is not there. This part is just 0 now because b is 0, and we only have this part. And when we apply the second boundary conditions, which is y at 1 plus y prime at 1, that's just a sine square root of lambda plus square root of lambda. Now that's cosine square root of lambda, and we have a here, and that's equal to 0. So in this case, again, we have it like this. We have, if we take it aside, we take a as a common factor, that just plus square root of lambda cosine square root of lambda. Again, A cannot be zero, otherwise the whole differential equation is just zero. And we want this one here to be zero, and that will give us the non-trivial solution. And this, again, this is our characteristic equation. So we can rewrite it as sine square root of lambda equal to negative square root of lambda cosine square root of lambda. And this basically, if we move this one to the left side, and we can call this the characteristic equation. And if we want to find lambda, we can find that lambda probably is equal, not probably, but this is what equals to negative tan square root of lambda. And the solution of this equation will give us the eigenvalues. And usually these kinds of equation can be solved numerically. So these are two examples that we did so far. And I just want to highlight one thing here, that here for this problem, assume that lambda is greater than 0. Because if we, probably you'll be asked this question in the homework, whether lambda is an eigenvalue or not. And that question is basically, we're only solving for non-trivial solution. So if at certain value, lambda does not give us just a trivial solution, we do not consider that value as an eigenvalue. So thus we just exclude that value. And in this case, if let's take it aside here. Oops. If lambda, let's change the colors. If lambda happen to be 0, then our differential equation will become just like this: y double prime equal to 0. And you know, if you, from what we learned before, if we use just the eigen equation, that just alpha square equal to 0, and we basically have two repeated solutions, and they are equal to 0. And our general solution will look like just like this. We have just a constant, and since they're repeated solution, we'll have that constant multiplied by x. If we substitute boundary conditions here, where we have y at 0 equal to 0, that would be just, obviously is C2, sorry. And where y at 0 equal to, that would be just C1. So C1 equal to 0. So now our y is C2x, but if we use, so the second boundary conditions which basically says that y at 1 plus y prime at 1 equal to 0. And if we plug these values into this one here, we already know that C1 is 0. So that would be just C2 plus C2 and equal to 0. And that just means that C2 equal to 0. And basically the whole differential equation equal to 0. So that's why in this case, for example, we say that lambda equal to 0 is not an eigenvalue. Hope that's clear. And if it's not, that's still fine. And now let's try to shift gears here and speak about other topic that will guide us to understand more the expansion, the eigen expansion and eigenfunction expansion. So now we speak about inner products and vectors and functions, vector space and function space. And since what I'll be saying will sound quite far from what we're doing so far, I just want to draw the big picture from now and then move into this inner product thing and come back to this big picture again, which basically we try to understand how we can basically do the eigenfunction expansion. Oops, no, eigenfunction. And all what that means, basically, we're trying to reach a conclusion of power series where our solution should be expressed in this form anyway, that and times phi n. So we want to find eigenfunctions and then express any function using this, and that's where we're heading right now. But we start from something that looks a bit far, not that far, but we'll hopefully we'll connect the physics of what we're doing. So inner products of two vectors. Vectors are something that we can actually visualize and see. So basically, when we speak about vectors, when we speak about, for example, two vectors here, u, for example, that's equal to 2 and 1, and oops, and vector v, that's equal to 1 and 1. So these two vectors, basically, we can we can apply the inner products, or what we call the dot product of these two vectors, which is basically u and v, and this is basically how we express the inner product. We have two curly brackets, and inside them we have u and v, and that's just basically we multiply 1 and 2 and 1 and 1, and that's just elementary school vectors analysis. So that's just 2 plus 1, and that's equal to 3. And that's what we mean by the inner product of vectors. Another property of the inner product, as you can see, we're multiplying this. So if we have 4 that multiplied by one of the vectors, let's say vector u times v, then that's just equal to 4 times u and v. And that would be, for example, we have 4, and we already found the inner product of these two, and that would be just the 12. That would start to, now it sounds very trivial, but once we go to functions, it will start to make more sense, and this one will be a bit easier. The last concept here in terms of vectors and the operation is the length of a vector, and they call it as well the norm of a vector. The norm of a vector, or the length of vector u, is basically the square root of the inner product of the vector with itself. So there's u and u. So square root of the inner product of this vector is basically the length of the vector. And for example, for this one here, we have u, which is 2 and 1. So that would be 2 times 2, 4 plus 1. So that would be just square root of 5. And that's the inner product, I mean, the length of the vector u. The fact that we have a vector, and the vector is expressed by these values here, nothing prevents a vector from being a function. So if a function can be a vector, or let me rephrase it, if a vector can be a function, then we can do the inner product of two functions as well. Now the definitions of the inner product of two functions is defined by this integral form here. And many times this r becomes 1, but not necessarily, but many times you can use this one as just 1. And in many of our problems, this a will be 1 as well. So this is the definition of inner product of two functions. So if we have any two function f and g, inner product is basically the integration from 0 to a r of x times f of g, f times g. That's basically the inner product of two functions. And now, since we are speaking about vectors that are functions, then we can speak as well about the length of the function. And the length of the function is basically just like what we did before. It's basically the square root of the inner product of the function with itself. So if we rewrite it again, that would be square root. The inner product of a function is basically that one. So it will be just the integration from 0 to a, and that would be f squared if r equal to 1, and that would be dx, and that would be the length of a function. And we'll need that as we move on. Now, I want to introduce Lagrange identity, which is quite related to this one here, to inner product. Basically, the Lagrange identity is the left side of our SLBV problem. We still speak about SLBV, though we spoke about functions, but we're still there. So that Lagrange identity, which is here what we defined as L, is that it's defined as this. And all what we are saying here for the Lagrange identity, that we need to find two functions, any two functions, y and t, y1 and y2, that satisfies the initial conditions, I mean the boundary conditions here, and these boundary conditions that the SLBV problem satisfy. And then, if these two satisfied, all what the Lagrange identity says, that's the inner products of this linear operator of y1 and the function y2 equal to the y1 and the inner product of y1 with the linear operator of y2. And just to remind you, from what we have from our SLBV problems, that our the L of y, or the linear operator, that's equal to just lambda y, where if we have r equal to 1. So if we assume, for example, here our first function is basically phi and let's use the blue. If we have our first function as phi, let's call it phi n, and this second function is phi m, and we have inner product between these two functions, the Lagrange identity says that we have phi1, and here we have the L of phi m. I know that sounds meaningless, but just bear with me. From SLBV problems, when we find any eigenfunctions n, that eigenfunction n is usually corresponding to an eigenvalue n. So each of eigenfunction will produce one eigenvalue. And all what that says that here, when we have any function y, and the linear operator will produce lambda times y, which is what we have here. So if we apply that one to this inner product, that L phi, that will give us just phi lambda times phi n, and then that's phi m, and that's equal to phi n, and here we wrote 1 phi n, and again that one is just lambda m phi m. And now again, I want to relate what I said with the scalar multiplied by an inner product, multiplied by a vector and the inner product. I just said we can factor that scalar here. Oops. We can factor that scalar out, and we can do the same thing with the vectors. So I mean with the function. So here we have an inner product of a scalar, which is lambda, multiplied by this function, and we have it in the inner product. So we can factor that out. So that would be lambda n phi n phi m, and that's equal to lambda m phi n and phi m. We can move these to the other side. So that would be lambda n minus lambda m. I'm taking this as a common, I'm taking this part as a common factor. And now that's multiplied by the inner product of phi n and phi m. And here I'm assuming that I have two eigenvalues, and two different eigenvalues, which means that the first one does not equal to the second one. So this part has to be 0. And what I forgot to mention, and I should have mentioned, is that the inner product between two functions, if that inner product or the dot product between two vectors or functions is 0, all what that means that these two are orthogonal or perpendicular to each other. So Lagrange identity, all what it says, basically, if we find two functions and we apply the inner product to these two functions, then these two functions has to be orthogonal. Anyway, orthogonal. And now I want to speak about applications of the inner product and hopefully try to relate it to the expansion soon. So we'll speak about first the application of the vectors, inner product for vectors, and then application of that inner product to functions. So whenever we have two vectors and these two vectors are, and the inner product, these vectors are 0, basically that means that these two vectors are perpendicular. So if we have u, and that u is basically 2 and 1, and we have v, and basically that v is -1 and 2, and we perform the inner product of these two, that would be -2 plus 2 equal to 0. So basically all of that means that these two vectors are perpendicular, and if we want to draw them, we can actually draw them like this. We have 2 here and 1 here, so that's basically how we draw vectors. And the other one is basically we have 1 here and 2 here, and these two has to be perpendicular. And if we want to normalize a vector, so if we want to normalize a vector, we have to divide it by its length. So to normalize it, and let me say to obtain the unit vector, we basically need to have our u and divide it by the length of that vector, and that way we obtain the unit vector, or let me call it E1 here. Basically, I want to mention that because that unit vector is important if we want to find a projection of that vector into another vector. So if we have a vector t and we want to project it, okay, vector, let me call that this 1, 1, and this 4, 4, I mean, and we have this E1 here. The projection of that one into this is basically the dot product of this vector t with this unit vector. So if we have that product or inner product, that t with this one here, and that will give us the projection, and let me call it P1 here. So that gives us the projection, and that's this one is just 1 and 0, so that would be just 4, and it just makes sense that this value is 4 and 4, so the projection is 4 here. So here, all what we're trying to do is that if we want to express any vector in terms of any other vectors, then we need to dot product, or to take the inner product of that product, if it happens to be t, with the unit vector pointing in that direction for the other vectors. Let's get an example, and then let's try to get to the point where I want to just deliver. So I want to make, so if we have two vectors, let's say vector u and a vector v, and I have a vector t, and that vector t is, let's say that's 2 and 4, and this is 2 and 1, and this one is basically -1 and 2 equal to equal to equal to. And I want, for the sake of, just for the fun, it's not for the fun, but I want to try to make a point anyway. So I want to find the projection of T on U and the projection of T on V. So what I want, to achieve these steps, I need to make 3 main steps. I need to unify or find the unit vectors or unit vector or normal, let me say unit vectors, or let me say normalize U and V. Second step, I want to find the projection of T on U and of T on V. And let's call it P1, which is basically, let me express it in terms of the unit vector, I mean inner product, which would be T times the, not times, but with the inner product of U, which is basically U divided by its length, and the projection of P2, which is basically T with V, and that would be, I'm just writing this so that because it has to be a unit vector. And the third time, not the third time, I need to basically the sum to express or represent the vector, just like what I did here, in terms of the projections. All what I need to do is now to get the P1 dot so yes, so basically once we have we need to multiply the projection with the E1 with the projection 1 plus the projection 2 with the E2, which is basically V, or we can write it as the summation of PIs or times EIs. We can write it CIs here, and we'll come to that why. So let's do these steps. And we basically, we first need to normalize. So let's normalize. And we have the length of the first vector, which is basically square root of the inner product of the vector with itself, which is 4 plus 1, which is basically a square root of 5. And the inner product of the second vector V, which is basically square root of 1 plus 4, and is again is square root of 5. So the unit vector of the first vector is U divided by square root of 5. And for the V, it's basically, let's add the arrow here, divided by square root of 5. And this is basically the first step. Now we need to find the second step. Let me add a blank page here. We'll be done soon. So we want to find the projection. And that projection is basically, let me call it P1, which is the T on U, is basically the equal to, let's erase this one here. Let's have the N here. So that's T times U divided by its length, and that's it, and that's just equal to, we have T is 2 and 4, so that would be we can factor the 1 over square root of 5 out, and that would be 2 times 2, 4, plus 4 times 1, again, that's 4. So that's basically 8 over square root of 5. And again, note that this is just a scalar, which is basically when you do an inner product, you only get scalar. The P2, and let's try to do it fast. That's V, again, divided by square root of 5. And that's equal to 1 over square root of 5. And that would be 2 times -1, which is -2, and plus 8, and that's plus. And that would be 6 over square root of 5. And let's raise this one here. So now we are done with the projection. So we need now to represent that vector and that 2 vector space. Okay, represent the vector in the orthogonal and that using those 2 orthogonal, vector space. And the way to do that, just like what we described here, that just the summation of the projections times the vector 1 plus the projection 2 times vector 2. So let's just write it here. That's PI projection times the EI, which is basically the unit vectors, which is in this case just U over square root of 5 and V over square root of 5. And now that just will be, we have the projection, which is the P1, which is 8 over square root of 5. Let's change the color. So that's 8 over square root of 5 multiplied by E1, which is basically 2 and 1, and that's 1 over square root of 5, and plus the projection 2, which is 6 over square root of 5, and that's -1 and 2, and we have a square root of 5 here. Note that now we can add these similar terms here. So this one with this and this one with this. And what we expect to end up with 2, 4. To end up with these 2 numbers here, just to check that what we're doing is correct. So now if we take the 1 over 5 as a common factor, because we have square root of 5 times square root of 5, and we have same here. So we'll take that as a common factor. And here we have 8 times 2 is 16 minus 6. So that's a 12. And here we have 8 times 1, that's 8, plus a 12, so that's 20. That's 16 minus, oops, so that's 10, sorry. So that's 10. And if we just divide by 5, that would be 2 and 4. And the point now is to ask this very valid question. Why? Why are we doing this? And how is that related to SLBV problems and the expansion? And these are very valid questions here. And the answer to this comes to the point when you apply these same concepts to functions. Let me reiterate what we did here. Here we had 2 vectors, U and V, and these 2 vectors represent what we called vector space or vector linear space. And we wanted to express another vector in terms of of the space that were created by these two vectors. And the way we did that, we found we normalized these two vectors, and when we found the projections of this one on these two vectors, and we summed the projections multiplied by the unit vector of each vector, which makes sense and simple. But as we said earlier, these vectors can be a function, and that function and then we can have a function space. Whatever, if we have two functions, and these two functions will create a function space, and they have a third function. I want to represent the third functions in terms of the space created by the first two functions. The concept, I mean, visualizing that one is not easy, but thinking of that as vectors and writing the steps for vectors and visualizing it enable us to move them to functions and do exactly same steps. And that steps here that I just did here for the representation of a vector in terms of two vector space is exactly what the expansion is when we come to the SLBV problem. Let's get an example here. So basically, if we have any functions, and here if we have any function, let's say a function phi n, or a function f, just phi. Let's cross this one. And we want to represent a function, let's call it f of x, in terms of that function. All what we need to do is to normalize this function here and find let me call it phi n. And the way to do it is basically just like what we did with vectors. I need to take the function and divide it by its length. And what's the length of a function? It's basically the function divided by square root of the integration from 0 to a, and a mostly 1. That's function squared. And that way we find the unit function, or normalization of that function. And then we find the projection of this function onto this. And the way to do it is basically, let me call it P. And in the slide and the lecture notes, these values were called CIs or Cs. But now let me call it C because it's just the projection. That projection is nothing but the inner product between that f of x with the phi of n. And what does that mean? That's just the integration from 0 to a. That's the definition of the inner product. So that's just r, which and many times that's just 1 times f of x times phi dx. And that's what the projection is. And at the end, the very last step, we basically take that projection and we multiply it by the unit function. And guess what? All what we did so far, though it looks a bit weird and strange, and I know that it's not very organized, but this one here is what you usually see in the slides. That's Cn times phi n, and that's y equal to this, and that's what usually we'll have summation here, but I just assumed the Einstein notation. If we have multiple functions, we'll have more examples here, but that's my point here that I'm trying to make, that the expansion of any function is basically very much like projecting a vector into two vector space. Now, in this case, it just happens that we have vectors, but it's possible to have a function and express it in terms of other functions, or what we call the function space. Let's move on. And we'll move to application of what we just said, which is basically using eigenfunction expansion to solve SLBV problem. And this is the form of expansion that usually this is the form of differential equation that we have, that we will apply the eigenfunction expansion to. we will have the linear operator of this form, which is very similar to what we did before. However, now at this time we have function here f, and if we have this one here, not that what we have here is not lambda, but we have a mu here, and this problem is not an SLBV problem. We need to form our SLBV problem from this, and then use eigen expansion to solve it. So what do we need to do to form our SLBV problem? It's very similar to solving first homogeneous term and then moving to non-homogeneous part. And to do that, we form it by just saying that our Lagrange identity, or the linear operator Ly, by definitions is basically equal to the negative, for example, if r of x equal to 1 equal to this, and that one equal to lambda y. We need to rearrange our equation, which is, for example, this case here, so that whatever this part here, we move all the all other things to our other parts or other functions to the other side of the equation, so that we only have this part here, and we solve in terms of lambda. The best way to do it is just move to an example. And I just want to highlight one of the main reasons of doing this and expanding a function in terms of eigenfunctions is that our eigenfunction here automatically satisfies the boundary conditions. And that's the main advantage. Once we write it in this form, it's just like a power series or a Fourier series or a Taylor series, but it's expanded in terms of eigenfunctions, and those eigenfunctions satisfies the boundary conditions, and we do not really need to change anything, except that we need to find these values here. Let's have an example. So the first example is about normalizing a function. So let's assume that we have this function here. I mean, this differential equation, and it's basically asks us to find the eigenfunction and then to normalize it. This is a very typical function, and now we know by heart that its solution is just a sine square root of lambda plus b cosine square root of lambda, and there's x here and there's x here. And we need to apply boundary conditions, and that would be equal to 0, equal to b, where we have b equal to 0. And now we need to apply the second boundary conditions. That's equal to 0. And that just means that we have a sine square root of lambda, and that's at 1, plus square root of lambda a times cosine square root of lambda, and that's equal to 0. And now this is just now the characteristic equation again, and we already know that, and we do not need really to go over that. And that just will be tan square root of lambda plus square root of lambda, and that's just the characteristic equation. And what we want to highlight here, that we have from this, we find that our eigenfunction, just like what we did before, is a sine square root of lambda times x. And the questions basically ask to normalize this one here. And what we did before to normalize this one and find phi n, all what we need to do is take phi and divide it by its length. And the length is basically square root of from 0 to 1, because that's this is the period that we have here. It's from 0 to 1. and that's the unit vector times itself, which is basically, now we have we'll have phi square here dx, and let's normalize it, and let's take this part aside. And here I just want to highlight we have a here, and here this a basically would cancel on the top and lower side, so I won't write a here, but I want to analyze this one here, just the integral. So this is basically, we have sine square root of lambda x, and that sine square is basically 1 minus, equal to 1 minus cosine square root of lambda x. The cos square of any cos square of x I want is equal to 1 plus cosine 2x over 2. So that this just trick to evaluate the integral. So that part will be just 0 to 1, and this one will be half minus half cosine 2 square root of, oops, let's rearrange it, raise it to make more space. So that's half cosine square root of lambda x. And now let's evaluate that one. Let's take 1/2 as a common factor. And when we integrate, that would be just 1. And now this would be minus, and here we have 2. Sorry, I forgot it. So minus 1 over 2 square root of lambda times sine 2 square root of lambda x. And this one here can be expressed as the following as well. We have 1 minus, we have 2 square sine 2 square root of lambda can be expressed as 2 times sine square root of lambda x cosine square root of lambda. And I do not really need to write the x because I already substitute the value of x by 1 here, so that there's no x here really. Yeah. And now I want to use one of the facts from the characteristic equation, which I should have write here. Here we have the non-trivial solution. Here you'll see that sine of square root of lambda equal to negative square root of lambda times cosine square root of lambda. If we take this one here and we basically substitute in there, we'll see that this sign can be replaced by negative square root of lambda cosine square root of lambda. And at the end, we will have this one will cancel with this, and the 2 will cancel with the 2. We'll have half times 1 plus cosine square root of lambda. And that's that. And this one, this part here should go into the phi n. So now at the end, I'm running out of space. Our phi n is square root of 2 times sine square root of lambda x divided by square root of 1 plus cosine square root of lambda. And this is our normalized eigenfunction. Now we want to test the expansion and what we did, what we said in terms of vectors and expanding any functions. So when we spoke about the vectors, basically what I was saying that it is possible to virtually expand any function in terms of any base functions or base functions, which is the one that we created, which is, for example, phi or the function space. And what we want to do now is we want to expand this very simple function, f of x equal to x. We want to expand this. And we want to apply the steps that we did before to expand this function. And here, all it's asking here, use the normalized eigenfunction found in the previous example to expand this one here. So we found that our phi of n, the normalized one, our phi of n is, again, square root of n sine square root of lambda x divided by square root of 1 plus cosine square. Let me remind you what were the steps are for to expand any function. First, normalize. Normalize your eigenfunctions. And what we did, we found this one, we found phi n. Second step, project, find the projection. And what does that mean? Let me write all steps, and then let me say represent. Or you can say expand. So the projection, again, is nothing but having our function that we want to expand, which is, let's say, f of x, take its inner product with our unit function now, not unit vector. And if you remember, what's the expression of the inner product? It's the expansion from 0 to a, and a here is just the interval, and here the interval is from x from 0 to 1. So now it's from 0 to 1, and our function here is just x, and x times phi n, and that's the way we find our projection. And let's evaluate that. So that's p equal to the integration from 0 to 1 times x times phi n, and phi n is basically, we have square root of 2 times sine square root of lambda x divided by square root of 1 plus cosine square. These parts are just constants, so we can take them out, and for simplicity, let me just call r equal to square root of 2 divided by square root of 1 plus cosine square root of lambda. I'm calling this part as r. So now we have r times the integration from 0 to 1 of x times sine square root of lambda times x dx. So I can just evaluate that simply by integration by parts. So if this differential part and this integration, so I have x here, and this part, I'll integrate this part, so that would be negative 1 over square root of lambda times cosine square root of lambda x, and that's 1, and this plus minus, and then now the projection becomes just r, and that's r multiplied by x, and we have a negative here, divided by square root of lambda times cosine square root of lambda x plus, now we need to carry out the integration of this one here, and that would be just 1 over negative and negative positive. So that's 1 over, and when you take the integration of this one, we have 1 over lambda times sine square root of lambda x. And all of that is evaluated from 0 to 1. And you can see here at 0, those will just cancel out, and at 1, we will have r minus 1 over square root of lambda cosine square root of lambda plus 1 over lambda sine square root of lambda. If we again use the characteristic equation, we can see that the cosine square root of lambda is just equal to negative sine square root of lambda over square root of lambda. So if we apply that, we'll see that this is just equal to 2 sine square root of lambda over lambda. And basically that's the projection. And the last step, represent or expand. And all what we mean by represent by that point is now that function, the expansion of that function, f of x or y, is now basically the projection p times phi of n. And here, if you notice that now p is basically a function of lambda, and lambda can be values here, so we can call it pn. So we'll have pn here, and that would be let me call it 2r times sine square root of lambda n over lambda n times phi n, and phi n is basically what we already found. So and you need to write it down, and that's basically the expansion. I know it looks very complex and quite hard, but basically that's the expansion of this very simple function f of x equal to x in terms of eigenfunctions, and these eigenfunctions are these. And the main advantage of that one again is that the eigenfunction by definition satisfies the boundary conditions. So once we do that, it looks very similar to power series, but now all the coefficients satisfy the boundary conditions, and we do not really need to substitute anything here. So now we have another example, and it's the last example that we'll be doing, and we'll be done. We want to solve this boundary value problem. And the first thing that we want to highlight, this is not SLBV. We need to form our SLBV problem. All right. So that's important here. Or sometimes they call these non-homogeneous SLBV. Anyway, in any case, and the way to do it, we want to write our operator in this form here. We want to write our operator L, which is y, which is defined by what we knew before, negative y double prime. That operator in itself, I mean, we want to find what this equals to, and that's equal to, if we need to look at the differential equations for this part, we need to move this one here and this one here, and in that case, that would be just equal to 2 y plus x. And again, let's just try to draw the big pictures. This one here from the SLBV problem. So we want to find that's Ly. It's basically, by definition, is equal to lambda times y. So this is more like the homogeneous part of it. We're solving it and try to relate that one to it, just like what we did with other problems. We solve the homogeneous part and then try to solve other parts. And now we want to solve it using expansion. This part will be more like equal to 2y plus x, but all of these, let me erase it because that is so that it is more correct. We want to express all of these parts as expansion of eigenfunctions, which means that this one here, the 2y, let me rewrite it. This lambda now, this y need to be written as an expansion, as something like this, and as expansion of the eigenfunction. And this one here, again, it needs to be written in terms of expansion of eigenfunctions, not in. And that one, again, needs to be expansion of eigenfunction. We already expanded that one. And let me call it Cn Pn, where this Cn is actually what I wrote before as Pi, which is the projection. So that's what we want to do. We want to solve that equation. We form our SLBV problem. And what we want to find is B, because our y at the end will be expressed as Bn times Vn. And that Bn now, we can move this one to the other side and find Bn, and that would be just Bn equal to, we can cancel this one and this one and this one, Cn over lambda minus 2. So the first step that we want to find all of these values now, to find Bn and this Cn value, which is nothing but the projection, we need to find the eigenfunction. So let's solve the eigenfunction from SLBV problem. So the eigenfunction now is L equal to lambda y. And again, we're solving more like the homogeneous part, the homogeneous. So that would be y double prime plus lambda y equal to 0. And just like what we did before, this is just a sine square root of lambda plus b cosine square root of lambda. And our boundary conditions are basically, we have y at 0, it's equal to 0, and that's equal to b. And we know that b equal to 0 now. And if we apply the other boundary conditions, which is this one here, and that's equal to, just we'll take a as a common factor, and that would be sine square root of lambda plus square root of lambda cosine square root of lambda. Again, from here, from this point, we can actually find that our eigenfunction, it's not normalized yet. Our eigenfunction is just a sine square root of lambda x, which is, we have almost same problem that we did before. So it makes sense that to be the same. And our characteristic equation will have these relations here from it, just like other problems. Square root of lambda cosine And our characteristic equation basically looks like this. 10 plus square root of lambda. Let me add one more page here. So now we have found our phi, where our phi is a here sine square root of lambda x. And since here our differential equation and boundary conditions is very similar to what we did, and oops, that's different. Oops, let me double check. It's very similar to this problem, which means that the phi is the same, so the normalization is the same, so we can use same phi. So our phi n, just like what we did before, our first step is to normalize, and upon normalization, which is basically phi n equal to phi divided by the length of the function, which is basically the integration of the the square root of the integration of the function square. And we already found that one phi n to be square root of it's this one here, square root of 2. Square root of 2 times sine square root of lambda x divided by square root of 1 plus cosine square root of lambda, and that's our phi n. And second step is to find the projection. Projection of what? Projection of the function, or of the f of x part of this non-homogeneous equation, which is projection of this part here. And I'll look at this part here because we rearranged the equation. So I want to find the projection of this one, or yeah, the projection of this one and then the expansion of that one here. And we already found this one in the previous problem, which we used to have f of x equal to x, and we found the expansion and the projection of that one. So we already found that, and the projection, just to remind you, that's I called it pi or pn, and which is basically our cn, and that's equal to the inner product of the function itself with the normalized eigenfunction. And we already found that value in the previous problem, and it is basically this one, r. That projection is basically r times, I believe we have 2 sine square root of lambda divided by something, divided by lambda n. So, and that's and divided by lambda n. And last step is basically to have our this one formed our cn, and now we need to find our bn by this equation here. Oops. So yes, now at the very last step, we need to find our bn, and that our bn based on the equation that we found for this special problem, that's cn divided by lambda n minus mu, and that mu in this case is just it's just this one here is 2. So the final solution now is just Bn equal to, let me write even including the Rn, so that's the square root of 2 sine square root of 2, not square root of 2, that's square root of lambda, square root of lambda n divided by lambda n square root of 1 plus cosine square root of lambda and that's multiplied by 1 minus 1 over lambda n minus 2. And our solution, final solution, is basically y equal to the expansion of Bn times the projection, the eigenfunction, which is basically equal to this one here that we have, Bn times phi n, which is what we already found or provided here, which is this one, this value here. And okay. And with that, I believe we ended the first part of these lectures. I hope that was useful. And if it's not, I understand. Thank you and enjoy.